Hey kids, look again, another video that starts off, recall Calc 1. So, differentials. Remember that was a topic right before the hated related rates. So when we first introduced derivatives, remember we talked about how a change in x, delta, or change in y over change in x, or delta y over delta x became this small d, dy dx. When the change in x's and y's became very small. And then remember this kind of graphical interpretation of a differential in 2 dimensions. So if I have a point A and a y value that is shared by both the line and the curve, when I change A by a little nudge, right, just a small change in x, that corresponds to a change in y, right? So the change in y between when I plugged in A and when I plugged in A plus a little bit is this horizontal distance here. That is the change in y. But notice that when I plug in that new x, that x that is just a little bit further away from the point of tangency, when I plug that value into the tangent line, I don't get exactly the same value as the curve, right? It's off. The change in tangent line, right? The change in the tangent line from the original y height to the new close to original time y height is the change in the linearization or the differential, right? This distance. As long as dy is a small change in y, dx is a small change in x. So we're talking about make this x here being very small. So maybe this was 3 and delta x was 0.01. So this is 3.01. Using the tangent line as an approximator to this curve, right? There's the error. That's not too bad, right? The error right there, that's not terrible. So the small change in y, right, the change is approximated by the change in the tangent line, the linearization, right? So here is like saying y2 minus y1. But remember y1, remember the linearization at the point of tangency is the same value as the function at the point of tangency, right? Right? F of A is equal to the tangent line at A, right? The linearization at A. So I can replace those two values. And then look at what I have here. Can you see what that is? The y2? That is the equation of the tangent line at A. But notice what happens there. Whoops, sorry, I didn't mean to. A minus A cancels out, and I'm just left with dx. And then notice what happens with the f of a's. They also cancel out. So I am just left with f prime of a times delta x. That is what we call the differential of y. If y, as long as y is a differentiable function, the differential, the small change in x, is the independent variable, and the differential y, the estimated change in y, is equal to the derivative times your really small change in x. So we're just going to take that into 3D. given a function in two variables, the differential is very similar, but it is a sum of your partials, right? So the differential of the function z, or the differential of the function f, right? We can use both of those names, is a sum of f prime with respect to x times dx plus f prime with respect to y dy. So here's kind of like the corresponding picture in 3D, right? Where we're talking about those tangent planes and the actual change in D from the curve to its tangent plane and the differential there. This is a vocabulary word that you're going to want to make note of. The total, think sum. The total differential, we can also write in the del notation. The differential of the function z is the partial derivative of z with respect to x times t times dx plus the partial derivative of z with respect to y times the really small change in y. So let's do a couple of examples. So to find the differentials, and again, I could say total, but I don't have to, total differentials. The differential in z is a sum right, of partial x. And what is partial x? Partial x here, now this is a product, right? So I'm going to have to product rule this. So partial x would be holding y as a constant. So it is the first function times the derivative of the second, and the second is in terms of x, so secant squared 2x times 2. Oh, I did not do a good job with my spacing, did I? Plus the second function times the derivative of this, but remember that y squared is just a constant. So the derivative of e to the x squared plus 4 is e to the x squared plus the derivative of a constant, which is 0, times the derivative of x squared, which is 2. So the first times the derivative of the second plus the second times the derivative of the first. That all supposed to go in this big parentheses. And then here I have another product rule problem. But this time I'm going to keep y constant. So keeping y constant, right, I have the first function times the derivative of this. The first function, which is 0, sorry. So plus the second function times the derivative of this with respect, though, to y. Remember, x squared is going to be a constant, so I'm going to have 2y times e to the x squared plus y squared. Oh, it's just terrible. My spacing there. Let me write this a bit better. 2 e to the x squared plus y squared secant squared 2x plus 2 e to the x squared tangent of 2x. That's all times dx plus 2y e to the x squared plus y squared tangent of 2x, all times dy. Now the next one, I gave you 3 variables. So I have 3 variables, and again, think total. So I'm going to take the differential of u, but that's going to be one differential plus another differential plus a third differential. So taking the differential with respect to t means hold the other ones constant, right? R to the 6th and x squared are constants. With respect to r, t cubed and s squared are constants. And with respect to s, right, this is really s to the negative 2. Times the constants. Okay. That's really all there is to it. We will do some more examples in our live session. See you then.